Good morning. This is conversions day 2. So conversions day 2. And today we're going to look at octal and hexadecimal. So let's look at octal first. Octal is a base 8 number system where the digits are 0 through 7. Okay? And how we convert to and from octal and to and from hexadecimal is through binary. Binary will be our middle person that we go to, both ways. So let me show you a base 10. Let's go from base 10 to octal. All right, so let's go from decimal to octal. And let's take a decimal number maybe that you're familiar with, like 114. Randomly made that up. And now I'm going to convert that to octal. I said binary would be our middle ground. So what we're going to do is we're going to take 114 and convert it to binary first. So we're going to convert this to binary first and then convert it to octal. That's our plan. So from the last video you've seen that 114, I'm just going to convert it to binary. A little review here, a little preview or reviewing the content. It's going to be 1, 2, 4, 8, 16, 32, 64. So it's 64. So take 64 away from 14. I get 50. 32 and 16 is 48, and 2 is what we're looking at. Let me just double check. 32. We get 18. Then we take 16 away. And we get 2, and then we take 2 away, and we get that. So the binary number for 114 is 1110010. Okay? Now, what we're going to do is take that binary number. I'm going to write it again. I got plenty of space here. And I'm going to break it up, starting from the right. Over here a little bit. Okay, thank you. Starting from the right, I'm going to break it up into 3s. Every 3 gets broken up, okay, because these are going to become my octal digits. So starting here, it's 3, 3, 3. It doesn't matter that this doesn't have any more. It just doesn't matter. Now I'm going to make mini ratio tables because I told you the largest digit this could be is 7. So 1, 2, 4. The largest digit it would be is 111, which is 7. And I break this up to 1, 2, 4, and then that just gets a 1. So now we do each digit separately. This is a 1, so that's a 1. This, when I add it up, the binary, it's a 6. So that's 6. And this is a 2. 114 in base 10 is 162 in base 8. Just like that. Let me recap it. We went to binary. From the binary, we broke it up into 3s, starting from the right. So you'll get these 3 bits. Break it, these 3 bits, break it, and if there's any other bits, that's okay. And these become our digits in octal. Let's try another one. Let's try another one like, let's go your favorite number, why not? Let's go 69 in base 10, and now we're going to go to octal. Whoa, to octal. So 69 in binary. If we go to binary as our middle source, 1, 2, 4, 8 using the ratio table, 16, 32, 64. So it's 64 and 5. So that's our 69 in base 2. And now I'm going to do exactly what I did above. I'm going to break it up into 3 starting with the right. So 3 bits, and I still have 1 left over. So this becomes 1, that becomes 0. If I look at 1, 2, 4, remember every section for octal gets 1, 2, 4 as a ratio table. And this one's 5. So this becomes 105 in octal. Do you guys have any questions? I can't hear, so it doesn't really matter. All right, nice. Let's go the other way. Let's go octal to decimal. So we're going to go, let's take something like 162 in octal and see what that is in base 10. Once again, we're going to use binary. And we're going to actually do the opposite of what I just did. And let's follow my opposite thinking. I'm going to break the digits up. Get out of there. This is going to be 1, 2, 4, so it's a 1. This one's going to be 1, 2, 4, so it's a 6, so that's 4 and 2. And this one's going to be 1, 2, 4, and this is a 2. You have to put the preceding zeros here, okay? The only time you don't need preceding zeros is on that first one. So this big binary number is 1, 1, 1, 0, 0, 1, 0. Now put it all together. Put together. Okay? Now, after I put this all together as one big number, guess what I'm going to do? A big Marashio table. 1, 2, 4, 8, 16, 32, 64. So it's going to be 64, 32, and 16 plus 2. So 64 and 16, I'll add quickly, that's 80. That's 112, 114. So this is 114 in base 10. Whoa! Let's go back. Wasn't it 114 in base 10? Oh, there it is. So I did it nice. Okay, I did it very nice. So it's going to be, once again, to recap what we've done. We break each digit up into 3 binary numbers for each digit. Then, once I have that, remember to add preceding zeros except for that first one. Put this number all together right here. We're going to put this number right here all together. What you got, put it together and do a big Marashio table on it and do it like you would. Let's do one more. Okay. Let's do, like, let's say 77 in base 8, and let's see what that is in base 10. Okay? So, break the digits up. I'm going to break these digits up to 1, 1, 1, 1, 2, 4, 1, 2, 4. For 7, it's got to be that. So my binary number is 1, 1, 1, 1, 1, 1. If you notice, 7 is 1, 2, and a 4. 7 here is a 1, 2, and a 4. So now if I do a big Marashio table, 1, 2, 4, 8, 16, 32, 64 would be the next one, so this must be 63. One less, because it's all ones below it. I taught you that in class. If not, you can add up all these. 32 and 8 is 40, 56, 63. It works either way. That's octal. Hexadecimal is done very similarly. This is what the computer uses. Hexadecimal, hex for short. Hex is base 16. So how do you represent 16 digits? Well, you have to introduce some letters. So if I counted in hexadecimal, it would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then I need 15 digits plus the 0. Okay, over here. I need 15 digits plus the 0. So 11, 12, 13, 14, 15. I can't represent 10, 11, 12, 13, 14, 15 as one digit. So what they do is they introduce letters. 10 is an A, 11 is a B, 12 is a C, 13 is a D, 14 is an E, and 15 is an F. So a normal hexadecimal number could be like 13F. That's a normal hexadecimal number. Another hexadecimal number, weirdly, would be Dad. All right? And of course, 1 in hexadecimal is the same across all of them, including binary. 1 and 0. They stay the same. So let's do a little conversions here. All right? Let's convert hexadecimal. Nope, let's go decimal to hexadecimal first. Let's go decimal to hexadecimal first. Okay? So a decimal number like 120. We want to find out what that is in hexadecimal. Once again, our middle step, this is going to look very much like octal. All right? Our middle step is binary. So we're going to go to binary first. And it's going to be 120, remember, is 1, 2, 4, 8, 16, 32, 64. 64 and 32 is 96. 96, this is too much. 96 and 8. Well, let's see. 96 and 16 is 12. Carry the 1. It's 10. No, I could get this 16 in there. So I'm at 112. I need 8 more. So it looks like that's it. Let me just double check. 64 and 8. No. It's 32 and 8 is 40. That's 104, 120. Perfect. So it's 1111000. Perfect. The only difference now between octal and hex is what I'm about to say. Hexadecimal, you break instead of 3, you break into 4s, starting from the right. So I would break this up like that. 4 and whatever is left. And now the little Marashio table you put under it goes 1, 2, 4, 8. 1, 2, 4, 8. You might say, well, why is it like that? Well, check it out. If these were all 1s, it would be 8 plus 2 is 10, plus 4 is 14, plus 1 is 15. There's 15 digits. All right? So here we go. This would be 8 as a digit, and this would be 7 as a digit. So 120 in hexadecimal is 78. You might be saying, well, you didn't get a letter. Remember, not all of them have letters. All right? Let's try one more to see what's happening. All right? Let me give you a decimal number like 260. And let's find out what that is in hexadecimal. So I'm going to go to binary first. It's going to be 1, 2, 4, 8, 16, 32, 64, 128, 256. This is going to be 256. You're not going to get a letter in this one. 256 and 4. So my binary representation of 260 is that. The next thing I taught you, or you should do, is to break it into 4, starting with the right. So here's a 4. 1, 2, 3, 4. Break it up. And now do mini Marashio tables. Well, the first one's done for me. That's 4. This is 0 because there's nothing there, and this is a 1. This would be 1, 2, 4, 8 in each one. 1, 2, 4, 8 in each one. So this is 104 in hexadecimal. Lost my place. Let's go the other way. The other way, I'm just going to reverse the process. We're going to go hex to decimal. All right. So here's a hex number. You ready? I'll put an F in there. F8. Hexadecimal, I want to know what that is in decimal. So what I do is I break them up. I'll break the digits up right here, and this will be 1, 2, I'm sorry, going the wrong way. 1, 2, 4, and 8. How do I get F? Remembering that F is 15, it's all 1s. Now 8, 1, 2, 4, 8 is just an 8. Put it all together. Get this big binary number. Put it all together and do a big Marashio table on it, and voila, we're done. 1, 1, 1, 1, 1, 0, 0, 0. So this would be 1, 2, 4, 8, 16, 32, 64, 128, and it's going to be whatever this all is. Looks like one, I don't know. I don't know. 64 and 16 is 80. 80 and 40 is 120. This looks like 248. Double check my math, please. But it looks like 248. Let's do one more. Let's do one more. Let's do DA in base 16, or DA in base 16, or hexadecimal is what in decimal? Well, let's go to binary first. Okay, once again, break it up. A is 10, if you remember. So 10 in my Marashio table is going to be 8 and a 2. D, A is 10, B is 11, C is 12, D is 13. So to make 13 in my Marashio table, is 8, 4, and 1. So that's 13. Now